21.2 Heat Pumps and Refrigerators. In this session, we will cover several key topics regarding the movement of thermal energy. We will begin by comparing heat engines to heat pumps, and then introduce the Clausius statement of the second law of thermodynamics. To measure how well these devices work, we will define the coefficient of performance for both cooling and heating modes. We will also look at real-world applications, like refrigerators and air conditioners. Finally, we will distinguish between reversible and irreversible processes to understand why all natural processes fall into the latter category. To understand a heat pump, it helps to first recall how a heat engine works. In a heat engine, energy naturally flows from a hot reservoir to a cold reservoir, and we extract work from that flow. A heat pump or refrigerator essentially does the opposite by reversing this natural direction. It transfers energy from a cold reservoir to a hot reservoir. Because this movement is against the natural flow of energy, it cannot happen spontaneously. Therefore, a specific amount of work input is required to accomplish this transfer of energy. The schematic shown here illustrates the energy flow in a heat pump. The device takes in a certain amount of energy, which we call the magnitude of heat from the cold reservoir. It then expels a larger amount of energy, the magnitude of heat, to the hot reservoir. According to the first law of thermodynamics, the energy expelled to the hot reservoir must equal the sum of the work done on the device and the energy drawn from the cold reservoir. The diagram shows the heat pump as a central circle, with work entering from the side and heat moving upward from the cold base to the hot top. The second law of thermodynamics can be expressed through the Clausius statement. It tells us that it is impossible to construct a cyclical machine whose only effect is to transfer energy by heat from a cold object to a hot object. In other words, you cannot move heat from cold to hot without doing something else. This means that work input is absolutely mandatory for the process to function. A perfect heat pump, which is shown in the diagram as a device with no work input, where the heat out equals the heat in, is physically impossible. When a heat pump is used for cooling, such as in a refrigerator or an air conditioner, we measure its effectiveness using the coefficient of performance. For cooling mode, the goal is to remove as much energy as possible from the cold space. The coefficient of performance is defined as the ratio of the energy transferred at the low temperature to the work done on the heat pump. Mathematically, this is the magnitude of the heat from the cold reservoir divided by the work. A typical, high-quality household refrigerator usually has a coefficient of performance between 5 and 6. In heating mode, the objective changes. The goal is now to transfer energy into a warm interior to keep it comfortable. The coefficient of performance for heating is defined as the ratio of the energy transferred at the high temperature to the work done on the heat pump. This is calculated as the magnitude of the heat delivered to the hot reservoir divided by the work. For a typical unit, these values are around 4 when the outside temperature is above -4 degrees Celsius. However, the efficiency of the system decreases significantly as the outdoor temperature drops. Let us look at how these devices operate in the real world. A refrigerator uses internal coils to absorb energy from the food inside. External coils, often located on the back or bottom of the unit, then release that energy into the kitchen air. Air conditioners work similarly by using interior coils to absorb energy and exterior coils to release it outdoors. This process relies on a circulating fluid that is compressed to become hot and high pressure, then expanded to become cold and low pressure. The image shows the back of a refrigerator, where these coils transfer heat to the surrounding air. In this example, we consider a refrigerator with a coefficient of performance of 5.00 and a power input of 500 watts. It contains 500 grams of water at 20 degrees Celsius, and we want to find how long it takes to freeze it to 0 degrees Celsius. To solve this, we define the time interval as work divided by power. From our definition of the coefficient of performance, work is equal to the magnitude of the energy extracted divided by the coefficient. The energy to extract is the sum of the energy to cool the water and the latent heat to freeze it. Substituting these values into the equation, where time equals the energy extracted divided by the product of power and the coefficient of performance, we get approximately 83.3 seconds. In practice, this time is longer due to energy leaks. We now turn to the difference between reversible and irreversible processes. A reversible process is an idealization where a system can return to its initial conditions along the exact same path on a pressure-volume diagrams. In such a process, every point along the path must be an equilibrium state. In contrast, an irreversible process does not meet these strict criteria. It is important to note that all natural processes are irreversible. A classic example is the adiabatic free expansion of a gas, where a gas expands into a vacuum. While the temperature remains constant, the process cannot be reversed without changing the surroundings. The diagram illustrates adiabatic free expansion using a container with insulating walls. Initially, a membrane separates a gas from a vacuum. When the membrane is punctured, the gas expands to fill the entire volume. To reverse this and return the gas to its original volume and temperature, an external engine would have to do work to compress the gas. This work, combined with the heat transfer to a reservoir needed to maintain the temperature, changes the state of the surroundings. Because the surroundings cannot be left unchanged, we have proof that the original expansion was an irreversible process. To summarize our discussion, heat pumps and refrigerators are devices that move energy from cold reservoirs to hot reservoirs by using work input. The Clausius statement of the second law is fundamental, because it forbids the spontaneous transfer of heat from cold to hot. We use the coefficient of performance as a metric to define the ratio of useful energy transfer to the required work. Finally, while we study reversible processes as useful theoretical models, we must remember that all real-world thermodynamic processes are irreversible. We conclude with 2 review questions to test your understanding. First, consider why the coefficient of performance of a heat pump decreases as the outdoor temperature falls during the winter. Think about the energy required to extract heat from an increasingly cold environment. Second, explain how the Clausius statement of the second law of thermodynamics relates directly to why you must plug in a household refrigerator and provide it with electrical work to keep your food cold.